Alright, good afternoon. How's everybody doing?
Good. How you doing?
Awesome, finishing my lunch. That's a good thing. Alright, let's start off by talking about homework 2, which you turned in and I've graded and given back to you. A nice job on homework 2. I think people are in good shape with these concepts. I graded question 1.5, number 2 and 10, 3.2.2 and 3.3.4. So let me talk briefly about all of the homework questions just to make sure that we're all up to speed. So section 1.5 is looking at summations and products. So question 2, so 2a had a typo in it that was mentioned. This should be the sum from I goes from 1 to 3. And anytime you see a summation, you're really just saying evaluate this expression first for I equals 1, then for 2, then for 3, and then add them up. So you get 4 answers from here, right? So this should be, for n equals 1, this would be, well, let me write this down. Sum from I equals 1 to 3 of I to the n. So for n equals 1, this is basically 1 to the 1 plus 2 to the 1 plus 3 to the 1, which is 1 plus 2 plus 3 is 6. For n equals 2, this is 1 squared plus 2 squared plus 3 squared, which is 1 plus 4 plus 9, which is 14, and so on. Section B, sum from I equals 1 to 5 of 20. So this is saying take this expression evaluated for I equals 1 is 20. For I equals 2, this is 20. For 3, for 4, for 5, add them all together. So this is a funny way to write the number 100. And then C is basically the same. It's n to the j instead of j to the n. And then D, sum from k equals minus n to n of k. And so let's just pick one. Let's pick, for example, n equals 3. This is the sum from k equals minus 3 to 3 of k. Well, if k is minus 3, then k is minus 3. If it's minus 2, minus 1, 0, 1, 2, 3. Add those together. And everything cancels. And so for all your different n's, this turns out to be just good old 0. So that was just sort of messing around with summations, getting a feeling for them. Question 4, I did not grade, but it looked like people had some pretty good success with this. So this is asking you to verify for one particular value of n this summation rule, which generalizes, which is if you have two expressions or two terms added together and you take the sum from 1 to n, it's the same thing as taking the sum of those individual expressions and adding them together. And so we're asked to show that the sum from I equals 1 to n of ai plus bi equals these individual sums. So something like this, and I'm going to put some parentheses in here just to be clear that we're trying to take this summation of this sum and show that it's equal to this summation plus that summation. And this is a little tricky to do in general. To show that this is true for any integer n bigger than or equal to 1, we need to use something called mathematical induction. We're about 2 weeks away from that. But for the case where n is, for example, equal to 3, this is pretty straightforward if we just work with the definitions. Now again, remember, we can't show that this is equal to that by showing that this is equal to blah, and that's also equal to blah when we do some stuff. Okay? We can't manipulate both sides and come up with, 2 equals 2 and then conclude that these were equal. But what we can do is we can start with, say, the left side. And we can write down things that this is equal to using what we know about arithmetic and summations, and in particular commutativity. And if we eventually show that this is equal to that, then we're done. So anytime you're trying to show something like this, try to simplify. Occasionally you find a solution by making things more complex, but generally the trick is going to be to try to simplify. So let's start off with this expression, and let's just write out what this summation means. It means basically take a1 plus b1, and then add a2 plus b2, and then add a3 plus b3. That's just a direct interpretation of what this summation symbol means. Plug in I equals 1, plug in I equals 2, plug in I equals 3, add them together. And now, knowing what we know about algebra, we can modify the arrangement of these things and say that this is a1 plus a2 plus a3 plus b1 plus b2 plus b3. So this would be like definition. This would be commutativity of the addition operation. And now I'm going to use the definition of this and say, well, this expression here is just the sum from I equals 1 to 3 of ai. And this is just the definition of the sum from I equals 1 to 3 of bi, and I'm adding those together. And so that's the definition of summation. And I can throw in parentheses without harm. And so I have shown that this sum is equal to that sum plus that sum, right? Now that's not exactly a proof, but it's a demonstration for that particular value of n. And a slight modification of this with the machinery of mathematical induction will let us prove this for all n. Okay, we'll do that later. All right, and then same thing for pulling a constant out, right? Write this expression as a1 plus a2 plus a3, multiply by c, distribute the c using just plain old arithmetic of numbers to write this as ca1 plus ca2 plus ca3, and then reframe that in this notation, and we've shown that the left side is equal to the right side. Alright, question 10 was looking at products instead of summations. So let me just write these down. Alright, so the first one is a plug and chug, right? K equals 0, that's 2 to the 0, k equals 1 is 2 to the 1, k equals 2 is 2 squared, k equals 3 is 2 cubed. Multiply them together. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 1 times 2 times 4 times 8 is 64. I had, I think, 3 students who all got this far and then added them up instead of multiplying them and got 15. Because we usually do summations, but product is another thing, right? So that's the pi for p for product, sigma, Greek letter S for sum, addition. All right, this one I suggested don't just multiply everything out, try to think about it and not do too much work, okay? So if we write this out, if k is 1, this is 1 over 2. If k is 2, it's 2 over 3. If k is 3, it's 3 over 4. If k is 99, it's 99 over 100. And if k is 100, it's 100 over 101. I think we looked at this on Monday. And things cancel. And this is just 1 over 101. So yeah, it does get really small. It does approach 0. And if you tried to do this for infinity, the limit of that would be 0. Okay, but we're not doing limits yet. We're just doing a product of 100 expressions. And it turns out to be 1 over 101. You might also write this out as 100 factorial over 101 factorial, but you want to simplify that down. Factorials are usually very complex, and there's no way I'm going to do this on my calculator, right? My calculator blows up around 79 factorial. Do the cancellation. There's a nice simplified answer. All right, and then chapter 3, so 3.1, question 2, for each of the following propositions, identify simple propositions, express the compound proposition in symbolic form, and determine whether it is true or false. So the world is flat, or 0 is an even number, so I'm not going to write these out, but for example, you could let F be the proposition the world is flat, and let Z be the proposition that 0 is an even integer. And then this would be the proposition F or Z, right? First proposition or second proposition. And that should be true if either or both of those propositions is true, and 0 is an even integer, so this whole proposition is true, even though it includes a nonsensical part like the world is flat. And if you're a flat earther, no offense intended. And so on and so forth. So 5 is a prime number, and 6 is not divisible by 4. Well, 5 is a prime, okay, meaning it's not divisible by anything except itself and 1. And 6 is not divisible by 4. So P could be the proposition 5 is a prime number. Q could be the proposition 6 is not divisible by 4. And this would be the proposition P and Q. Or Q could be the proposition 6 is divisible by 4, and this would be the proposition P and not Q. Up to you. And this turns out to be true because both of those halves of the conjunction are true. 3 is a member of the integers, and 3 is a member of the rational numbers, or the fractions. That is true. So fractions also include things like 3 over 1, which is just the whole number 3. So your integers is actually a subset of the rationals, because every integer can be written as a fraction, namely an integer divided by 1. Someone commented, if being a flat earther would excuse me from physics homework, I would totally jump on board. It's a good question, actually. Like, what would physics look like with a flat earth? It would take a few problems out of contention. But yeah, it would probably make your equations more complex. Alright, so that was question 2, is basically breaking statements up into pieces and finding little propositions. Again, I mean, this whole thing is a proposition. So if someone asks you to write a proposition that expresses this, technically you could say, let P be the proposition, 5 is a prime number, and 6 is not divisible by 4. That is a proposition, right? But usually we want to break it down into smaller pieces so that we can try to combine this with other compound propositions. Alright, so that was 3.1. Section 3.2, which was looking at truth tables and such. So construct truth tables of the following. So this is engineering 250 all over again, right? So P and not Q, for example. So the usual drill. And I'm going to suggest putting your truth tables in this order. This is sort of the standard way the truth tables are written, so that if these were 0 for false, 1 for true, this would count in increasing integer order. Technically your truth table is correct whatever order you put these in, okay? But this is the way that we'll always do it in the class. This is the way the book will do it. This is the way most things you find will do it. So if you get in the habit of doing it in this order, it makes your work more easily comparable to other things. It'll help when you're reviewing from the text and so on and so forth. So let's write a column for not Q. So we'll just negate this second column, true, false, true, false. And then let's write the conjunction. So we want this column ANDed with that column. So false and true is false, false and false is false. True and true is true, true and false is false. And so you do this for all the cases, all the parts of the problem. Had a number of students who seemed to do an or instead of an and here. And I don't think there was misunderstanding and versus or, because in other problems it seemed to be done correctly, but it was like the problem was misread or something. So this is critical, right? And there's a lot to keep track of. P and Q, ORed with Q and R, ORed with R and P. Okay? This, unlike coding, is not something to do late at night. Okay? Coding works great. Sometimes you need your brain to be pretty exhausted, or at least in a different state, right, where you're thinking more abstractly. CSE215, not the case. Okay? This is all about detail. So nice clean sheet of paper, write out all the columns, right? Make a column for P and Q, make a column for Q and R, make a column for R and P. Maybe take those and circle them or highlight them, and then take the disjunction of those three columns, right? And that keeps you in good shape. All right, and then 3.3, we're talking more about logical statements and such. So question 2, construct the truth table for this expression. So let me write down that expression. I'm not going to construct a truth table because that's like the questions from the previous one. So P, maybe I will write it. P and not Q, or R and P. Okay, so this is X. Give an example other than X itself of a proposition that is equivalent to X. Okay, so we want some expression which has the same truth value as this in all cases. Let's go ahead and do the truth table. And I'm going to switch to zeros and ones. And I will skip a little bit of steps, P ANDed with not Q. So we need P to be true, and we need Q to be false. And then R ANDed with P, so that's just these first two, this first and third column need to both be 1. So that's going to be a 0 everywhere else. And then we have to OR those to get X. So this looks like 0, 0, 0, 0, 1, 1, 0, 1. You can use zeros and ones. We're computer scientists in here, so if I see a 0, 1, I'll assume it's false and true. Alright, so we want an expression for X other than this, but with the same truth values. How do we do that? Well, make yourself a K-map, right? You've had Engineering 250. If you can simplify this expression, you can find a different expression which has the same truth value. That's what we mean by simplifying, right? So one way to do that is to make yourself a K-map. So do P down here and do R and Q and fill in your ones and cover your ones with rectangles and write the corresponding expression. I can fake it by having done some K-maps. Looking at this top section, I can see that P has got to be a 1. If P is 0, I know that X is automatically 0. So P has got to be a 1. And then I'm going to AND that with something that gives me this bottom part. Well, this bottom part is going to be 1 if either Q is a 0 or if I'm down here where R is a 1. So there's an expression that's logically equivalent to X, but it's different from X in that, you know, it's doesn't have the same form. Another way to do this is to use algebra. So take this and OR it with that. Well, distribute this across that term. So P and not Q ORed with R. And then you can AND that with P and not Q, ANDed with P. Well, P ANDed with P will just become P. And now you've got two big long things ANDed together, and you can try to combine those. And this is the other way that we simplify equations in Engineering 250. We usually skip over it. Something called SAR, Systematic Algebraic Reduction. And it's using these identities, right, page 58 of our text, or, you know, chapter whatever in our 250 course, that let us combine these things, distribute, cancel, cancel something ANDed with its negation, and so on and so forth. And that can lead us to a simplified form. So different possible answers there, different ways to get there. The next two are a little more interesting. Give an example of a proposition other than X that implies X. Okay, find some proposition, let's call it H, which implies X. So we want to find some proposition such that if that proposition is true, X is also true. And we know X is such a proposition. If X is true, X is true. Okay. But it says, give an example of a proposition other than X that implies X. So what did people come up with for this? Go ahead and post some chats if you had ideas about this. P and R. Why would P and R imply X? Because if P and R is true, this whole thing is true, right? Because it's a disjunction. So just knowing that P and R is true, that's enough to guarantee that X is true. Similarly, you could also say P and not Q. Well, that's enough to guarantee X. Because if P and not Q is true, then this disjunction is true, which means X is true. So there's two different expressions, different from X, that if either of those is true, we know that X is true. Okay, so that's an implication. That's something that implies X. Part D says, let's find a proposition that is implied by X. Give an example of a proposition other than X that's implied by X. So find a proposition H such that if X is true, you're guaranteed H is true. So yeah, if P is true, then P or X is true, right? We have some fancy name for that. That's good inspiration from the book. All right, if X is true, what else do we know is true? We know all of this is true, but what else can we say? And here's an idea, since we know that X is equivalent to this, suppose we know that this statement is true, what else can we say is absolutely true? This is one of these page 58, 59 things too. Suppose I tell you it is sunny and blah blah blah. What can you conclude? What's a simple proposition you can conclude is true? You can conclude it is sunny. So if X is true, for example, we know P is true. Oh, you shouldn't forget class today. We had a proposition. If today's Wednesday, we have class, remember? You should write it on the wall. So this would be one solution for part D, right? If X is true, then we know P is true, and we can see that from the truth table. Anytime that X is true, P is also true. It turns out we also have another possibility. If X is true, then we know Q is false or R is true. We need a proposition saying today is Wednesday then. Alright, so those are possible answers for part D. So this is playing around with the difference between equivalence, implies, and implied by. Right? So when you say this, you're saying if hypothesis, then conclusion, right? The hypothesis implies the conclusion is implied by the hypothesis. Alright? And that's different from a biconditional or a logical equivalence, which says A implies B and B implies A. Or it says B is implied by A and A is implied by B. Either of those mean A and B are equivalent. So this was looking at different forms of that. Alright, we have bash code for class. Good deal. Alright, so that was 3.2, 3.3, number 2. Alright, number 4. Suppose that X is a proposition generated by P, Q, and R equivalent to P or not Q. Write out a truth table for X. So this was just an exercise in understanding that, you know, we could have a function of 3 variables that doesn't depend on one of the variables. Right, but you can write this out as a function of 3 inputs, P, Q, and R, and you can write out what the disjunction of those is, right? And you get something like this: P, Q, R, and there's P or not Q, right? And it's just the R's don't matter, right? And so back in 250, right, if we were to make a K-map for this, we would have pairs of ones, right? If there was a 1, there'd be an adjacent 1, and we could box those out and end up throwing away our R, and write this just as P or not Q. Alright, and then question 6, find a proposition equivalent to P or Q that uses only conjunction and negation. So if you're trying to switch between disjunction and conjunction, think De Morgan. Alright, so P or Q. Well, De Morgan's theorem tells us something like this: the negation of P or Q is the same thing as the negation of P conjuncted with the negation of Q. So P or Q is the negation of P or Q, right? Double negation, which is the negation of, and we can plug all of this in place of not P or Q, negation of P ended with negation of Q. So there's an equivalent expression using only negations and the conjunction operator. And that's the kind of stuff we do with De Morgan's, and it's pretty reminiscent of what we did with saying, for example, that NOR gates were universally complete, and that you could represent any logic circuit just using NOR gates. Okay, same idea. Well, we can represent any equation using just negation and conjunction. Right, so same kind of manipulation. De Morgan for the win, always, I agree. Alright, any other questions on that homework set? Alright, well let's continue talking about proofs then. Alright, so question, is implication a fancy word for equivalence? No, it's actually not. Implication is something like this. P implies Q, which is the same thing as saying if P, then Q. Okay, equivalence, P is equivalent to Q. That's a biconditional. So it says P implies Q, but also Q implies P. Okay, it's a stronger state than just implication. So P implies Q says if P is true, Q is true. Equivalence says, and the only time Q is true is if P is true. Alright, good question. Alright, so let's play around with proofs. So we started talking about direct proofs on Monday. Direct proofs, we basically started off with some things that we knew were true, and we did stuff until we got to what we were trying to prove. So direct proof. Start with what you know. Proceed till you get what you want. It's direct because we're starting with something that we know is true, usually a hypothesis. Alright, so you start with what you know is true, and you proceed forward until you get to the thing that you're trying to show. So let's find something to play with. So let's play with this one. Not P or Q, comma, S or P, comma, not Q, implies S. Alright. So we're given not P or Q, we're given S or P, we're given not Q, and we're asked to prove S. Alright, and typically we write these vertically. So this is a theorem that given this and this and this, we can conclude that. Okay, so let's do a direct proof. So direct proof looks like this. Start off by writing down what you know. So what do I know? Well, I know not P or Q. That's a hypothesis. Now I don't actually know if not P or Q is true in the grand scheme of things. My microphone's way over there. I don't actually know if that's true or not. Okay? But to prove that this, and this give me S, I need to show that if this is true, and this is true, and this is true, then S is true. Okay? How do I show that? Well, I'm going to start off by supposing that this is true, and this is true, and this is true, and I'm going to argue and show that S is true. Okay? None of that means that this is true, or this is true, or this is true. We're not showing that. We're showing if this, and this are true, then S is true. Okay, that's a subtle but really profound difference. So a hypothesis doesn't mean it's true. It means that in this proof we're assuming that this is true, and we're going to assume this and this are true, and then we're going to show that under those assumptions S is true. So let's write down our other hypotheses. I switched to an uppercase Q. Alright. That's all we can write down for now. We can't write down S because we don't know that S is true. And as soon as I write down S, everything after that depends on S being true. So if I write down S and 10 steps later I come up with S, what have I shown? If S is true, then S is true. I haven't shown anything. Okay? But I've only written down these three things. And as long as I argue logically from here, whatever I get to, if I get to dog, I've proven that if this, and this are true, then dog. Right? Okay, so let's go logically from here. So I've got not P or Q, I've got S or P, and I've got not Q. What might be a possible fourth step? And let me bring up my page 59 again. Alright, so I've got these three statements. Is there anything else I can do? And I'll give you a hint, since I've written down this and this and this, all three of these things are true. So I also know this is true, and I know that is true. I also know that this ANDed with that is true. And this ANDed with that is true. And this ANDed with that is true. And this ANDed with that is true. Everything above here is true. So a conjunction of two things that are true is also true. So do any of these rules apply? Disjunctive simplification, I like it. Disjunctive simplification says if I know that P or Q is true, and I also know P is false, then Q must be true. That should make logical sense. This first statement says one of these two things is true. And this says, hey, that first thing is false. Taken together, that second thing must be true. And this form of it says, hey, those first two things, one of those is true, and that second thing is false. I guess the first thing must be true. So if we look at this statement right here says, hey, either not P or Q is true, And this says Q is false. So we must be able to conclude not P is true. So someone suggested disjunctive addition on number 2. Disjunctive addition lets us start with a single term and then or something else with it. But we already have an or of 2 things here. So I'm not sure addition would help us there. But simplification, I think, does. So we have not P or Q, and we also know Q is false. We can conclude not P. And that's disjunctive simplification between 1 and 3. Alright, so now we've got not P. That's a new factoid, which we know is true. We know P is false. What can we do now? Another disjunctive simplification. In particular, we know that S or P is true, and we know P is false. That's a perfect setup for disjunctive simplification right here. So S or P is true and P is false, S must be true. The reason? Disjunctive simplification, and that's 2 taken together with 4. And what have we done? From these 3 hypotheses, we proved S was true. We were asked to prove, given these 3 hypotheses, S is true. We've proven what we were asked to show. That's the end of our proof. QED, perfect. Alright, so that's a direct proof. That's what we played with a little on Monday. Start with what you know, argue logically, try to prove what you're trying to prove. So in this notation up here, yes, the commas are ands. So when you see this, and this is how the book writes these theorems, it means given this, and that, then we can conclude this. So all the stuff on the left side of the arrow taken together concludes the thing on the right side of the arrow. Yeah, exactly. QED is a Latin version of mic drop. Perfect. Alright, so indirect proofs. This is a different way of proving the same thing in this case, but a very different feel to it. And sometimes an indirect proof works a whole lot better than a direct. There's some things we're going to prove that we really don't see a way to do with a direct proof, but they may fall out really quickly with an indirect. Okay, so let me give you a feel for an indirect proof first, and then we'll dig into the details of why exactly this works. So prove not P or Q, comma, S or P, comma, not Q, implies S. All right, an indirect proof is a proof by contradiction. This is a really powerful technique. You're asked to prove that S is true. I'm going to assume that S is false, and I'm going to show that something absurd happens. And assuming we want to live in a world where absurdities don't happen, we'll be forced to conclude S must have been true. So we're going to assume S is false, and we're going to show that that leads to nonsense. and therefore S must have been true. So let's see what this looks like. Let's write down what we are assuming is true, not P or Q, S or P, not Q. Those are hypotheses. I'm going to write down not S, and my reason is going to be this is the negation of the conclusion. Yeah, I agree. Absurdities are what make life great. So we know this is true and this is true and this is true because we're assuming they're true. They're their hypotheses. Given these things, we want to show that S is true. So I'm going to assume S is false, and we're going to see what happens. Okay, this is the negation of the conclusion. I'm assuming that this is a true statement, not S, which means S is false. Well, I know that S or P is true, and I know that S is false, so that tells me P must be true. Right? So that's disjunctive simplification of 2 together with 4. S or P is true, S is false, so P must be true. I can do that again. I know that either not P is, I know not P or Q is true, so either not P is true or Q is true. Well, I know that not P is false, right? Because P is true, so I know that Q is true. So this is disjunctive simplification of 1 taken together with 3, right? Not P or Q, sorry, 1 taken together with 5. Not P or Q is true, not P is false, and so Q must be true. But now, what have I got? I know that not Q is true, and I know that Q is also true. So the conjunction of those must also be true. Right, this just follows from 3 and 6. But I have a theorem that says not Q ANDed with Q is false. There's a fancy name for that. Let's find it. P and not P is false. So that's negation. Well, what have I proven? I've proven that false is true, because everything that I write down here is true. Well, if we prove that false is true, that's an absurdity. Believe it or not. So this is a contradiction. So here's the symbol I use for contradiction. I don't think that's standard, but I just write this sideways crosshatch, contradiction. Because false should not be true. All right. The fact that I reached a contradiction means that there must be something that went wrong in here. Well, maybe I made a logical error, but I did not, right? These 3 statements I wrote down as true because I was trying to show what happens if those are true. But this I wrote down sort of tentatively. I said, let's negate the conclusion and see what happens. Well, if I negate the conclusion, I prove that false is true. Ergo, this must not be a true statement. Not S cannot be true, because if it is, I can show that false is true. So since not S cannot be true, not S must be false, S must be true. And that's what we were asked to show. So that's the end of the proof. All right, so that's a different feel from a direct proof. And it may look like we did the same work. We did 2 disjunctive simplifications just like in the direct proof. But in our next example, we'll see that sometimes indirect proofs feel very different from direct proofs. But let me take one more look at what we did here. What we really showed was that if S was false, then false was true. Right? We showed that if we assume not S, we can prove that false is true. Well, take the contrapositive of that, and not false implies not S. Not false is true, not S is S. So showing this is equivalent to showing that true implies S. Well, we know that true is always true, so this is equivalent to S. So logically, proving this is the same thing as proving that, because those are identical statements. That's the twisty-turny passage that looks identical approach to indirect proofs. But we're really doing a direct proof of the contrapositive. Right? We're showing that the negation of the conclusion leads us to false. Right? And if this is true, then we can also conclude that S must be true. All right, so let's use this. So a lot of what we're going to do next is proving things about even and odd numbers. Okay, so evens and odds, we're talking about integers, because it doesn't make sense to ask if 3.7 is even or odd. So we're dealing strictly in the realm of integers, and let's define exactly what we mean by an even and an odd number. So what's the definition of an even number? So an integer n is even if there exists an integer k such that n is equal to 2 times k. And so I'm throwing in some of our symbology from past classes. An integer n is even if there exists an integer k, right, k in the set of z, such that n is equal to 2 times k. So 10 is even because we can write 10 as 2 times 5. Negative 50 is even because we can write negative 50 as 2 times negative 25. And negative 25 is an integer. So is 0 an even number? Yes, it is. 0 is an even integer. Because we can write 0 as 2 times 0. And 0 is certainly an integer. Alright, n is odd if there exists a k in z, an integer k, such that n equals 2 times k plus 1. So 10 is not odd because we cannot write 10 as 2 times an integer plus 1. But 11 we can write in that way. 11 is 2 times 5 plus 1. So 11 is odd. And negative 1 is odd because it's 2 times negative 1 plus 1. Right, so negative 1 is odd. Positive 1 is odd because it's 2 times 0 plus 1. So these are our definitions that we're going to use for even and odd. And we're going to do some formal proofs with this. Alright, so here's our first theorem. Prove that if n is an even integer, then 3 times n is an even integer. For example, 3 times 4 is 12. 3 times 100 is 300. If n is odd, this doesn't happen. 5 is odd. 3 times 5 is 15. That's also odd. But if n is even, 3 times n is also even. Alright, so how do we prove this? Let's do a direct proof. Now this is a conditional statement. If n is even, then 3n is even. There's a proposition, there's a proposition, this is a proposition. Anytime we want to prove that P implies Q, what do? We assume that P is true, we argue logically, and hopefully we end up showing that Q is true. If we can do that, we're done. So first step in a direct proof is generally going to be assume the hypothesis. Okay, so we have to identify this is the hypothesis, this is the conclusion. So step 1, n is even. Why? That's the hypothesis. Well, what the heck can we do from there? We really don't have anything, you know, on page 58 or 59 that applies to, you know, n is even. We don't have anything in the earlier parts of the book. We don't have anything in our notes. There's really only one hope for how to proceed here, which is let's use the definition of what it means to be even and see if we can get somewhere with that. Okay, this is a puzzle. So, n is even means there exists an integer k such that n equals 2 times k. So I'm going to say there exists an integer k such that n equals 2 times k. Why? That's the definition of the term even. Alright, at this point it's useful to keep in mind what it is you're trying to prove. We're trying to prove 3 times n is even. Well, I've just done something. I've just written down n in a different form. And kind of out of desperation, the only thing that occurs to me is let's see what 3n looks like if we write n in this form. That's perfectly legal to do. That's just algebra. 3n equals 3 times 2k. Why? That's algebra, substitution, using step 2. Step 2 said n was equal to 3k, so I can say 3n equals 3 times 2k. Well, I'm going to expand this and say this is 6k. And I'm going to rewrite that as 2 times 3k. Okay, I'm going to make an observation. And this is a little bit sort of overboard on beating the point to death. But for our first few passes through proofs, let's be explicit. I'm going to make the observation that 3k is an integer. Now, how do I know that? K is an integer. If I take an integer and multiply by 3, I get an integer. How do I know that? I'm just going to say properties of integers. If I take an integer, multiply by 3, I get an integer. It's something called closure. But the key here is this observation that 3 times k is an integer. And combined with step 3, what can I say? 3n is equal to 2 times an integer. Well, I'm just going to write that down as a separate step, just to be as wordy as possible. 3n equals 2 times an integer, right? And that's just sort of combining steps 3 and 4. Well, if I've written 3n as 2 times an integer, what can I say? 3n is even. And that's the definition of even. And so by starting off with n is even, I have shown that 3n is even. That's the end of my proof. Alright, so that's a direct proof. 3 times an even number is even. By the way, when you're asked to prove something, it's useful, to me at least, to see if you believe it before you try to prove it. Right? The act of convincing yourself can help you figure out how you might prove it. So take a few even numbers, multiply them by 3, see if you end up with something even. Alright, so we've proven if n is even, then 3 times n is even. Let's prove that the product of 2 even numbers is even. We show that an even times 3 is even. Let's show that an even times any even number will also be even. And if you don't believe it, then try to find a counterexample. Right? So someone asks, what if I don't believe it? So if you're asked to prove something, try to come up with some examples, convince yourself that it's true. If you don't think it's true, look for a counterexample. And the process of trying to find a counterexample will very often help you see why it must be true, assuming it's not a typo on the question. Okay, prove that if m and n are even, then m times n is even. Well, you know, in this proof that we did, this 3 just kind of came along for the ride. I can do this exact same proof with an m in here, and you should work through this on your own. Well, when I do that, I'm going to end up being m times n is even. And it turns out an even number times anything is even. I don't need m to be even. I mean, m was odd here. And in fact, I don't need to use any properties of m other than it's an integer to show that m times n is even. But let's do something a little trickier. Prove that if m and n are odd, then m times n is odd. All right, Let's assume our hypothesis. 1, m is odd. 2, n is odd. Those are both hypotheses. Alright, where do we go next? Let's use the definition of an odd number. If n is odd, there exists an integer such that n is equal to twice that integer plus 1. So, there exists a k in z such that m equals 2k plus 1. That's the definition of odd. Okay, important detail here. This always costs a few points if you miss it. I want to use the fact that n is odd and say, well, n is also twice an integer plus 1. I cannot say n is equal to 2 times k plus 1 unless it's the same k as up here. Okay, if I didn't write this down, if I didn't have step 3 there, I could write a step 4. There exists a k in z such that n equals 2k plus 1. Right? By itself, not a problem. By itself, not a problem. But if I'm going to put both of these in a proof, I'm going to get myself in trouble. Because this k is not necessarily the same as that k. And if I write down m equals 2k plus 1 and I write down n equals 2k plus 1, I'm implying m and n are the same number. And there's nothing up here that says m and n have to be equal to each other. So I really don't want to write this down. So here's what I can do to keep myself honest. There exists a j in the set of integers such that n equals 2 times j plus 1. Definition of odd. Okay, that's really critical. Because as soon as I write down n equals 2k plus 1, I've got more nonsense. I've made a really restrictive assumption, which is that m and n are the same number. Okay, so now I've written m is 2k plus 1, I've written n is 2j plus 1. And we're going to do the same thing we did in the previous proof. While we're trying to prove something about m times n, let's multiply them. So mn is 2k plus 1 times 2j plus 1. And let's do algebra. So that's 4jk plus 2j plus 2k plus 1. That's algebra, and it's also the substitutions from 3 and 4. And keep your eye on what you're trying to do. We're trying to show m times n is odd. Well, we've shown that m times n is 4 times that plus 2 times that plus 2 times that plus 1. Is there any way to show that this is an odd number? Let's factor it. And this is just a trick, and after you've seen it and you've used it a few times, it becomes kind of second nature. I'm trying to show that m times n is odd. That means I'd like to show m times n is twice an integer plus 1. Well, there's a plus 1 over here. If I could show that this was twice an integer, I'd be set. Well, guess what it is? This is 2 times 2jk plus j plus k plus 1. That's more algebra. And now let's make the observation that 2 times j times k plus j plus k is an integer. That's properties of integers. And so I've shown that m times n is twice an integer plus 1. That means m times n is odd. And that's just combining 6 with 7, and that's what we were asked to show. Let's see, 4jk is 2 times 2jk. I think that's what I did. Yeah. Alright, so there's a direct proof that if m and n are odd numbers, then m times n is odd. Alright, let's look at something that's easy to prove with an indirect proof, but hard to prove with a direct proof. Let's prove that if m times n is odd, then m is odd and n is odd. So if the product of two integers is odd, they must both be odd. And that's not what we proved here. We proved given this, then that. What we're trying to prove now is that given that, prove this. We're going in the opposite direction. Okay, if the product of two integers is odd, we want to prove that both of those integers must also be odd. And a direct proof is a little elusive. So we would start off with m times n is odd. M times n equals 2k plus 1, where k is an integer. And then where do we go from there? How do we say something about m just from knowing that m times n is twice an integer plus 1? I mean, we could say m equals 2k plus 1 over n equals 2k over n plus 1 over n. But it's not clear that this is going to lead us anywhere. We'd like to show that m is twice an integer plus 1. Well, I mean, we're kind of like sort of in that direction, but we're not really, this doesn't get us there. Okay? This is really hard to do a direct proof for. But a proof by contradiction, an indirect proof, is trivial. So let's try that. So statement 1, m times n is odd. Statement 2, not m is odd and n is odd. Okay, this first statement, that's a hypothesis. Second statement, that's the negation of the conclusion. Okay, gotta be careful how we negate conclusions. Don't necessarily trust your intuition here. Use De Morgan. We want to make a statement which is the negation of m is odd and n is odd. De Morgan tells us that the negation of this is the same thing as the negation of this, or the negation of this. That's De Morgan's theorem. Well, the negation of m is odd is m is even. The negation of n is odd is n is even. Well, we already did a proof which said if we take an even number and multiply it by anything, we get an even number. So if m is even, m times n will be even. And if n is even, then m times n will be even. And so we know m times n is even. And that's a prior proof applied to statement 4. And now we have a contradiction. M times n is odd, m times n is even. That's a contradiction. And once we reach the contradiction, we can say, well, this must be incorrect. Negating the conclusion gives us something false, therefore the conclusion is true, therefore m is odd and n is odd. That's the end of your proof. Okay, that may take some thinking about. It may take a while to sink in. But my suggestion is go back over these on your own, work through these, and think about what's going on as you're setting up the proof, and think about what happens when you reach the final end of the proof. How did you get from the setup to the end, and what does that mean? Okay, and this is what most of our proofs are going to look like. Direct proofs, we're going to start off with our hypotheses, we're going to argue logically, we're going to suddenly come to our conclusion. Indirect proofs, we're going to set up our hypotheses, we're going to negate our conclusion, work logically, come to a contradiction, and then say, okay, so negating our conclusion led to a contradiction, so our conclusion must in fact be true. And it's always going to be one of those two things. Unless we do a proof by magic, that's a different thing. All right, so your homework questions, are not looking at this level. They're looking strictly at these kinds of things that we started with, where you're given, things like that, and you argue through and you apply your laws of logic and so on and so forth. We're going to keep working on Friday with even and odd numbers and integers and playing around with those kinds of proofs. We'll work a lot with squares of integers. The square of an even is even, the square of an odd is odd, things like that. We'll also do a proof that the square root of 2 is irrational, that you can't write the square root of 2 as a ratio of two integers. It's a marvelous little proof. It goes back to the Greeks, and we'll pull that proof out for Friday. So work on your homework, bring questions for that to class on Friday. Look over these proofs, think about them, bring questions for those also, and we'll continue this on Friday. All right, have a good afternoon. I will see you next time.